Okay, welcome back. And so now we're going to do another example. In this example we want to take a limit as n approaches infinity of this thing. Okay, so we're going to use, we're going to simplify this a little bit and then use the limit laws. So this is going to be the limit as n approaches infinity, and I'm going to split this up into two fractions. So 2n over n, which is just 2, minus sine n over n. Be able to see this better. Okay, now using the limit laws, this is going to be equal to, well, just going to be 2, right? The limit of this minus the limit of this, so this is just going to be 2, minus the limit as n approaches infinity of sine n over n. Well, here we can use the squeeze theorem. We're going to have to use the squeeze theorem on this one, okay? Because so if we look at 1 over n, so again, sine, right? Sine n is less than or equal to 1 and greater than or equal to negative 1, just like cosine, right? It's a cyclic function that bounces between 1 and negative 1. And then if we divide everything by n, we get this. And so we get our nth term here, nth term here, and our nth term here. So we know that a sub n is less than or equal to b sub n, which is less than or equal to c sub n. So now we know that this sequence of numbers, right, the limit of this, all right, so the limit of a sub n as n approaches infinity, okay, hold on, equals 0, right? And likewise, the limit as n approaches infinity of c sub n equals 0, right? In other words, the limit of negative 1 over n is equal to 0, and the limit of 1 over n is equal to 0. So that means by the squeeze theorem, right? The limit as n approaches infinity of sine n over n must also equal 0. So that means that this limit here is going to equal 2 minus 0, which equals 2. And so that's the limit. So the limit of this expression here as n approaches infinity is 2. And that's it.